Welcome, everybody, to this next installment of Under the Surface, a podcast for computational chemists and other drug discovery personnel. I'm your host, Chris Williams. I'm the Director of Scientific Support at CCG. Here's my co-host, Dave Thompson.
Hello, I'm a super senior scientist, I think is how I describe
Super
myself.
senile, as we determined.
That's
That's what we determined this week.
Oh, I got demoted already.
And on the theme of super senile, we have yet another veteran of the field, Scott Rowland, who's joining us today. Thanks for being with us, Scott.
Oh, glad to be here. So I think it's a polite way of saying I'm an old guy in drug discovery and computational chemistry.
Well, experienced. Yeah. Welcome. You're listening to Under the Surface, a podcast where we have in-depth discussions on computer-aided techniques in drug discovery. So welcome, everybody, to today's installment of Under the Surface. I'm your host, Chris Williams. I have my co-host here, Dave Thompson.
All right, nice to be back, Chris.
And we have today a distinguished guest, Scott Rowland.
Oh, thank you, Chris. Thank you, Dave. Glad to be here.
And I've known Scott for at least 20 years.
Yes.
And you're a veteran of the computational drug discovery community. So can you tell us a little bit, Scott, about how you got here?
Yeah, sure. And I think, really when I was just first starting my scientific career, I was really trying to figure out how to put math and biology together. And I wound up in a biochemistry class and just fell in love with protein structure. And so wound up doing my PhD in a protein crystallography lab, University of Alabama at Birmingham. And this was really back in the very early days of structure-based drug design. And because I was interested in math and computers, they were like, hey, we want to learn how to do all this. And I've started off really just trying to learn about basic things like hydrogen bonding and things like that you use in structure-based drug design. And I used a small molecule database from the Cambridge Structural Database and got my PhD, wound up going to the CSD, did my postdoc, then came back, worked for a small biotech startup,
BioCryst. They're still
yes,
around.
This is where we met. Then, after a few years, I went to Millennium, and they got bought by Takeda, and I was there for 18 years, and then did early retirement, and I do consulting now.
No, that's it. So how do you like in the consulting?
I'm liking it. I really like it. It's nice because you get to focus on all the science, and not necessarily have all the things associated.
Other things associated with work.
Yes. The other things we will not mention.
Yes,
But
exactly.
You did just say, I haven't known you for as long, right? I haven't known you for 20 years. I've probably known you for 5 or 6 years at this point because I supported you when you were at Takeda. You skipped over a bunch there, right? I'm sure you have. So one of the things I'm very curious about is our field is not that old. So when you joined, were you getting in on the ground floor as people were beginning to understand the importance of what is now structure-based drug discovery? Right?
Oh, definitely. I think back in my early BioCryst days, or even as a grad student, there were people, you would go to conferences and people were like, oh, what drugs have been discovered with structure-based drug design? This is new. How are you going to do this? There's just a lot of doubt.
Yeah.
Because it was new, not really had been done. And of course, it's essentially, I'm old enough now that I can kind of see that, it's just pretty generally accepted that structure-based drug design is a very valuable tool for drug discovery. But I would also add, while structure-based drug design has really benefited drug discovery, we're really still just scratching the surface. There is just a ton more to do. Yeah. So there are still interesting things to do with it.
Was it very much an uphill battle when you were inside a company as like a new? I imagine you were sort of the machine learning of the time, and they were looking at these new upstarts with their fancy ways of approaching problems. Yeah, how was that process of convincing people?
Yeah, it was. I think it was a little bit easier in my BioCryst days because that was very much geared around structure-based drug design. Mm-hmm. So it was, so we were very much about doing that. Mm-hmm. I think once moved to sort of larger corporate environments, it was still kind of it's a little challenging sometimes to get people to believe. And, one thing I always believed very much in doing was really working very closely with the med chemist. And actually back at Takeda, we had a lot of,
you had a lot of interaction with
yeah,
them.
we actually had done a lot to make Mo easier for the med chemist to use. And they really adopted it, and I was at Takeda for 18 years, so I could really kind of see, the initial, maybe a little bit of doubt or skepticism, and when I left in 2020, it was going strong.
So did this change by convincing people, or by just having a newer generation come in? A bit of both.
Maybe a bit of both, and I think a good part of it was really just working with a chemist, and because we were a team. We were actually embedded with the medicinal chemists. We weren't really, in essence, that separate from them, and we were all of us really working together just to try and advance the projects and discover new therapies. So we were all in it together.
I know I appreciated, I think I can't remember if you gave a talk last year or a couple of years ago where you really talked about the customizations that you'd built out for your colleagues. And I very much appreciated that it was in consultation with them in the service of the science you were all doing together.
Yes.
And that is almost how it has to be, right?
Exactly. And I think, Chris, you mentioned we've known each other for a long time. I think there was a big emphasis. We did a lot of support work for lead optimization, but I think as the tools and everything have grown, we switched to doing like virtual screening and things like that to discover new chemical matter, and I think these things have really helped. And and I think there's also there's like more focus on like ADME characterization and you looking at chemical properties. So
and computationals help with that too.
Yeah.
So, I mean, in terms of teaching med chemists how to do this, there's a few barriers. There's using the software. There's the understanding of what the software can and can't do, what to expect of it. And there's also, I think, one thing that people fail to recognize in some ways, just the simple manipulation of 3D structures on a screen, right? Yeah. We're used to seeing them, right? We rotate them around, we can sort of imagine them. And of course, I think it's more difficult than maybe some of us modelers appreciate, because that's why we have 3D glasses and these VR things. It's all to overcome that problem. Yeah. And I mean, maybe from your perspective, you can tell us, when did you sort of see some med chemists kind of get it?
Yeah, it's I think in a variety of different projects, we were lucky. We had a lot of structurally enabled projects. We had crystal structures, or even would produce multiple structures with different ligands from the project. And I think what really makes things click for the chemist is you get some sort of shift in the SAR, and you can look in the structure and see it. And I think there's really this sort of click, and it's like, and I think the way I like to describe it is, the whole thing about structure-based drug design is looking at the active site from a crystal structure is, or even homology models. Actually, homology modeling has gotten really good, so I wouldn't dismiss that at all. But it really kind of provides the map, and that's really the way I would try to explain it to the med chemist is, take your chemistry, med chem knowledge, look at this map, this active site, and say, oh, there's like a hydrophobic patch over here. Oh, I can use this type of coupling and put some hydrophobic groups there. So, just kind of use it to kind of guide things. So
there's the complement to the map that they're all automatically generating and updating in their own brains as they have these design meetings. Yeah. Right? What do we know about what we just made last week? Yeah. What does that tell us about what the protein's going to do? And then when you have the crystal structure, you see it. And if you're lucky, it all kind of comes together and it's all self-reinforcing, which kind of builds your confidence in the structural hypothesis.
Yeah. And that was one thing that we really did with our customizations to Mo, was to really make it very easy for the med chemist to sort of load these crystal structures in, and also the models, things we kind of proposed or they proposed, and had it all like superimposed in the same reference frame. So really they could just kind of pull it up very easily and look at it.
Talking to some academic friends, and they've built out some open source packages, right? And they hold workshops, just like we do. They hold workshops. The user groups come together. The users of their tools come together, and they said they were increasingly frustrated because these people would tell them, "Oh, this seems very useful. Oh, I'm going to use this all the time." And then they would go back to their own laboratories, and because it actually wasn't that easy to do the thing, they would just revert back to my old workflow. And so you're right. It's the full. I need to be aware of the solution. I need to understand the solution. I need to adopt the solution. And ideally, the adoption piece is really some testament to how easy you've made it by being thoughtful about having that conversation with me about why am I going to do this in the first place.
And I have to say, even thinking back on my career, some of the best times I have had is back in the old days, we used to have graphics rooms.
Yes, I remember the one you had at Decatur. There with the silicon graphics machine in the corner.
Is I was just sitting down with a med chemist or two there at the graphics terminal, and just and of course, the beauty is now with the advances in computing, they can kind of do it. But there was really something magical about just sitting around the terminal and kind of talking about chemistry, what they could do, what was sort of present in the binding sites you could take advantage of. I think one thing I always try to encourage the medicinal chemists is really just looking at structure, because it is of huge benefit. You just learn a lot. There's insights. As I said earlier, it's like a map for what you can do. And time spent looking at protein structure. Of course, that's how I started off. That's how I got into
Yeah, well,
this.
I mean, you're kind of preaching to your own choir here. Time looking at protein structures, you spent your whole life doing it, so it's a good thing to do. I mean, it's true. If you're not looking at the structure, your competitor is, right? And even if you get like only a modicum of information from it, it's more than someone who's not looking at the structure. And with drug discovery, it's kind of there's a lot of gambling in some sort. Which route is going to give me fruition and results? You don't necessarily know.
Yeah. Oh, brief aside.
Yes.
We were talking about protein structures. So back in my early grad days, when I got interested in protein structure, so there was a publication in Annuals of Biochemistry. Jane Richardson. I don't know if you remember the old ribbon drawings she used to manually do. Well, this is old enough. It was back in the days you had to actually go photocopy articles and stuff. I still have that. And I met her at a conference one time, and I got her to autograph it.
Nice. Nice.
Yeah.
So you're probably old enough to remember the time when, even with a protein crystal structure, people thought, well, this is an irrelevant thing because the crystal structure is not the form of the protein in solution doing the job. There was and it's, in some cases it's probably true. Yeah. But I think with kinases, they've found that even the crystal form of the kinase still catalyzes. So you got the right structure.
I had to tell you this. This is, we always talk about in science, I think sort of classical experiments. And one of the, you probably may remember this, Chris, one of the first things I had worked on when I was at BioCryst is PNP, purine nucleoside phosphorylase. Really interesting because it turns out, because back in the early days, it was like, are these active forms of the enzyme? Well, really, really slick experiment that was done by one of the scientists, because PNP sort of catalyzes a reaction with some of the nucleosides. It turns out you could take the crystal of the protein, put it in a cuvette, put it in a spectrophotometer, and you could actually see, if you turn it to the right wavelength, you can see product being formed. Pull the crystal out, flatline, nothing. Put the crystal back in, and you start seeing. Cool. Just to sort of prove that it was actually active. Just really sort of classic experiments.
When the company started putting everyone embedded in the groups, like, look, drug discovery is so hard that none of you are going to solve it on your own. You guys got to work together.
The medicinal chemists and the computational chemists are they're having a little beef, and the biologists are in the corner just being like, "You have no idea."
Actually, one of our chief scientific officers at Takeda at one time said, drug discovery is the world's best team sport.
Yeah, it's one of the things I most enjoyed about it, just the sheer dynamism of having biologists in the same room as medicinal chemists. I mean, it's a multi-parameter optimization problem, and that plays out in the context of your group meetings, in your SAR planning, in your SAR discussions, in your planning discussions, and all that good stuff.
And I mean, that's kind of how you spent most of your career, as one of the nexus for this stuff.
Exactly. And I mean, it's, I can remember times we'd go to the coffee machine and bump into a med chemist and chatting about ideas. Oh, let's go back and look at it on the computer. So,
This is pre-COVID, of course.
Yes, very much pre-COVID. Very much pre-COVID.
But I mean, it's good that you had the corporate culture there, because I've been in some places where the comp chem division is in a different building, different group, and they don't really communicate with the med chemists very much.
Yeah, no, it was the wonderful thing about Takeda was it was all a good group. It was just fantastic working with all of them. So it was awesome.
Okay, so I just want to switch topics a bit, because now you're an independent agent, right? And you're working in the Hollywood of biotech, which is the Boston area, right, and Cambridge. So in your consulting work, I've always thought, there's a lot of companies that need a modeler for like 1 month every 2 years, right, to do this one little thing. Right. And so, is this been your experience? This is my fantasy. Is my fantasy true?
Yeah, it's been really interesting, and I think. And what has been fantastic for me is, I've from an early age, I've just always loved science, and so it's really enabled me to keep doing science, and I think it's really trying to help out, and I love biotech startups. Yeah, people get new ideas, they're trying to generate things, and trying to help them out. 'Cause they don't necessarily need a full-time person. They don't have software, they don't really have computers. And so, I can kind of provide a little bit of that and kind of help them get off to a running start. And it's amazing. I think sometimes some of the things that you can do that, don't necessarily take a huge amount of effort, but just make a big impact on what they do. About just sitting around the terminal and kind of talking about chemistry, what they could do, what was sort of present in the binding sites you could take advantage of. It's just a lot of fun to get on, pull up structures, talk to them, show them, what's going on with things, and if we can explain SAR they're seeing, it's just awesome. And they get, you can just tell, even just over teleconferencing, you can just see excitement in people's faces doing some of this.
Some of the most fun experiences I've had, we have our training materials, right? So we'll go visit a customer and we'll give them our training materials. And what we'll offer is, if it's a big enough group or if they're interested in doing this, we'll do the training materials, but with their structures.
Yeah.
And this is fun and exciting because you don't know if it's going to work.
Yeah.
Oh, yeah. Well, Chris, you came and did that with us.
Yeah.
I mean, it's So, and it was great. I've had the good fortune of working with some really fantastic medicinal chemists, and just some of the creativity and the solution. I mean, it's amazing. Some of the solutions they come up with for stuff. You would have thought, how do you sort of fit this thing in there? And it's amazing.
So we wanted to talk about pharmacophores, because the title of this podcast is Fun with Pharmacophores.
Yes.
Right?
Because they're exceedingly fun.
Extremely fun. So pharmacophores, it's actually defined by IUPAC. There's the set of steric and electronic features necessary for interaction with a biological target, or something like that. I paraphrased it. But definitely, when I go into a room and say pharmacophore, like at a training session, I get some people nodding emphatically, some people like looking like it's Greek, or is it what it is Greek? But it seems to be a concept that everyone knows about, but no one agrees upon.
Yeah, I think you're right there a little bit. I think conceptually, everyone kind of has some vague idea of what they think it is. It's just, I think it's getting down to the sort of formal kind of specification of it is then where because I think because like within Mo, the pharmacophore query engine, there's all sorts of flexibility with what you can do. And, I think especially in comparison, like back in the early days when you were doing ligand-based drug design, and it's just, and I think, we sort of, I think initially came up with the idea of pharmacophores when you didn't have crystal structures and stuff. So again, ligand-based design.
Yeah.
But, pharmacophores work fantastic with structure-based drug design too.
Well, yeah, that's an interesting point too, because I think now with lots of crystal structures, it gets very compelling to go get a crystal structure, run it through the complete SBDD workflow, but there's kind of a lost art of the chemist looking at their 2D diagrams and generating this 2D cartoon pharmacophore based on SAR observations and other stuff, and I think that's. I don't know if it's coming back, but it's something that I think I don't see as much as I used to.
Yeah, I think you and I talked about this. I think med chemists very naturally think this way. I mean, I've sat in enough chemistry design meetings and chemistry meetings. You get pictures of scaffolds with sort of colored balloons over different pieces and what they've learned with the SAR, and I think really what having the computational pharmacophore, for lack of a better phrase, it lets you do so much more with it. You can then start to apply it.
Well, it becomes actionable, doesn't it?
Yeah, exactly.
Yeah. Right.
Exactly.
But it must also be consistent with their exploration and their understanding. What's in the literature? What have we understood as a project team? And now it becomes. I mean, you're going to talk about this, I think, tomorrow or Friday. But you're.
Well, but I think tomorrow or Friday. But you're right. I think we presented, and it may partly our fault, is the pharmacophores is technology. You're going to click on these things. You got this screen up here. These funny colored spheres I've never seen before, and then I press a button and I go search your database, and it's like a Docker. And what dials do I have to push? But the idea that the pharmacophore in 2D, which is the ChemDraw drawing with the PowerPoint annotations, is really the same thing as a 3D picture of this. And maybe it's back to the whole, can you see something in 2D? Because chemists see things in 2D, no problem. I love their 2D diagrams, the structures. But I think when it gets to 3D, there's a couple things. They don't maybe understand why you want to do it in 3D so much. And then there's, of course, am I using the technology right? Then there's a question, do I have the bioactive conformation? Yeah. So all that stuff starts to, get in the way of them spending a lot of time working in the 3D. And as we said before, ChemDraw works. I know how to use it. I can get a nice picture that explains things quickly.
Yeah, and I think too, it's important to realize that pharmacophores aren't static things. As chemists make compounds and test them, it's very much a living, breathing thing, and you kind of add to it, and and especially if you start. Get to some point where you're starting to explore different scaffolds and things like that. It's really, as you said, Dave, it is something actionable. You can go and kind of test. I mean, certainly in a structure-based context, you can do docking and stuff, but I still think there is a benefit to that pharmacophoric description.
We had this wackadoodle line of research, and I credit this to Chris because I think the work you're going to present tomorrow on the psychedelics is where I first read this, but Chris described the pharmacophore as a meme.
Yeah, a meme for our understanding of binding.
Right, and think, right, so, you were at Takeda for 18 years. Think about the number of times you worked on a project, stopped working on the project, and then picked the project back up again later, right? The ideas that you'd encoded in that project in the beginning kind of got carried through, and everyone had that shared understanding, the mimetic understanding of the canonical features of your class of compounds that may or may not have been related to activity. And I think that's a really powerful idea.
Yeah. And I think not to beat a dead horse here, but I keep talking about looking at structure as kind of like a map.
Yeah.
And really the pharmacophore was kind of how like you sort of drawn your route in a sense.
Yes.
On the map.
Yeah.
As to how things kind of work.
Yeah.
What you discovered.
Yeah. 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 It has to be. So it sounds like you have or are in the process of building a map of kind of approved drugs. Is that true?
Yeah. So that's one thing I'm really interested in is really trying to take, and I'm doing this with crystal structures. So really trying to identify important features and think, even trying to think about concepts like, we talk about ligand efficiency in fragment-based drug design. Well, can we think about pharmacophoric efficiency? How many? So, like, you put up a structure in Mo or a ligand, and it kind of annotates that.
Yeah.
And we usually don't use everything. No. Some things don't get used. How much how much of different ligands and different targets get used, what's in common. And, it's just kind of a different, not to sound.
No, well,
technical,
actually,
but
no.
yeah,
Like
but-
it's just a modified version of ligand. Ligand efficiency is number of atoms, right? So let's get a little, more granular, or less granular in a sense, right? And not number of atoms, but number of features. Like instead of having 6 atoms for benzene, it's one thing. It's like and ligand efficiency is how many of these pharmacophoric elements. You might think of it as an alphabet of the pharmacophores that proteins like to see. They like to see, like a glutamate likes to see 2 donors here. Something this kind of motif of residues like to see a donor receptor, right? Yeah. And when you present a new molecule, some of its pharmacophore elements are satisfy the protein, some of them aren't. And what is the penalty for that? So ligand efficiency is number of atoms on interacting, but maybe a modified version would be pharmacophoric efficiency, and it would just be something similar, but the atoms group based on pharmacophore, not just every atom with the same weight.
Yeah. And actually, in some ways, Dave, it's almost like a return to my roots, as it were, because I was saying in the beginning, I kind of really started off very early, looking at like parameters like hydrogen bonding, looking at like aromatic stacking and all that type stuff. And this is really, in a way, kind of an extension of that. It's like, looking at this huge wealth of structures we've got now, and just seeing, in kind of a different context, how does all that sort of map out? So it's going to be interesting.
Yeah, I'm looking forward to that. I guess you get sort of like a pharmacophoric description, and the different types of pocket, different types of motifs. It'll be interesting to see how far that can go.
Yeah. Well, it's a super abstract representation. I wonder how much of what we need to know is kept in that representation and how much of it's lacking, because that will inform how useful this thing ultimately
That's right.
is. Right?
Is it fine? Is it fine-grained enough to actually find differences, or are we just going to find, every protein likes to see an receptor?
Exactly. Yeah. But that's why I think you're looking at approved drugs is kind of interesting, right? We know if you think about it as your map, right, that you keep talking about, we these are points on the space that we know we care about commercially, and the patients obviously use and value. So now we can think about where the super small piece of chemical space we've explored from that.
It could almost be like
concept.
a Lipinski's rule for pharmacophores in a sense.
Exactly.
Right?
Oh my goodness.
Exactly.
And after we just dissed rule-based methods, we're going to make our own.
Let's make our own.
It's going to be better, of course, because we made it. But I think it's a different way of looking at it. It'll probably give you a little bit of signal more than others. But I think it might be a little more might be a little more satisfying in just the atom efficiency things, which is number of atoms. This is more like like a benzene ring is got, like, it doesn't like water. When you put so the raw atoms might not be enough, but the fragments might actually tell us something.
Yeah, it's gonna be an interesting experiment to see what pops up.
Well, when it's done, man, you come back and you
next year.
Yeah, you tell us how it went.
So if we have an episode 2 on this, it worked. If we don't, we just quietly forget it.
Yeah, exactly. And we never heard from Scott again.
Excellent.
Sounds good.
Okay, look, so I think we better wrap it up. The sun's shining. We want to get out to the terrace and have some drinks and enjoy the rest of the evening.
Yes, definitely drinks.
UGM. So look, thanks, Scott, very much for coming on.
Yeah, thank you,
We
Scott.
hope to have you again sometime. And for our listeners, stay tuned for the next episode.
See you around.
Yeah, and
See you
thanks
around.
for listening to me ramble.
Excellent. It
not
was joyful. Thanks for listening to this week's episode of Under the Surface. Don't forget to subscribe to our podcast so you don't miss an upcoming episode. Until then, signing off.